Joe here.
And Mr. Milks.
Unit 9, kinetics and equilibrium. We're going to get into what those potential energy diagrams are in this video.
Page 10, 11, video number 4.
You got to know all the ins and outs of the PE diagram. Label them backwards, forwards, upside down. Be able to label them when the graph doesn't look identical to the ones that we have.
Yeah, I promise you guys, this one is going to take a little bit of practice, so you better practice.
And there's a lot more of it in the practice pack. So, but at the same time, if you've watched this video and paid attention, you should probably go ahead and do them, because there's really nothing to it other than labeling and interpreting.
And you have some models, and then Milks and MoNaCo have the answer keys for you to check.
And if you get stuck on something, be specific. We want to help you learn, but if you're like, yo, I don't get this, I'm like, what's this? Yeah. What is it that you don't get? Yeah. Not helping me out, help you. Help me help you by paying attention.
Seriously, to the details.
It's somewhere to start.
Seriously. Cool. All right, well, let's start off with this. Remember, heat is
energy.
Right? We learned this a while ago.
Yep.
Right? So we got to remember that.
So we're going to keep track of that chemical potential, that heat and that energy in our products and reactants and potential energy diagram. So this is like we're looking at a graph of a reaction.
Yes, over time. So let's draw a generic one for exothermic.
I'll write it.
And I'm going to talk it out. So we all know from earlier on, right, that exothermic reactions, heat is exiting the system. So if heat is exiting the system, it should have less heat or less potential energy at the end than it did to start. So I got to start high and then finish low. And I can see now that the product side on the back, reactants and products, the products finished with lower. Now we're going to leave it at that because this is generic. We're going to leave it at this. We'll actually get into this particular exothermic reaction later and tell you all the pieces in this slide or two. Okay, but this is a generic exothermic reaction. Okay, so now we need to do a generic endothermic reaction. Endothermic is heat entering the system. So if heat enters and then gets tied up into the bonds themselves, my products are going to have more energy than the reactants. So I got to start low and finish high. That is a generic endothermic curve with the reactants on the left and the products on the right.
That's it.
Okay?
You might see these with actual values along the potential energy,
and we're going to get
kilojoules per mole, and then have to do some subtraction or citing the number. What is the energy of the reactant?
Very not complicated thing.
If you're paying attention.
So let's just define some of these things before we go ahead and label them up.
Yep. Forward reactions are, right from left to right. Reactions on the left side, products on the right. These are what you're familiar with. These are all the chemical reactions that we've seen all year. Arrow points to the right. Reactants makes the products.
Right, but now we can go backwards. At some point this unit we will be going backwards.
Right.
We will have to read from right to left. Now the reactants, the products become reactants. So the reactants are now on the right-hand side with the products on the left.
But in reality, the situation is that you can take those products that you just made and force them to go backwards into the reactants they were becoming. In the previous units, we'd actually rewrite that equation from left to right again, so our arrow points to the right. But now,
we can just put a double-headed arrow
in there. Put a double-headed arrow, point the arrow the other direction. And you understand, listen, if I could take two atoms and put them together to make a compound, you can be pretty sure that you can take that compound and pull it apart to make those two atoms separate.
Right. Good. Now the activated complex is a single point on these curves that I need you to be able to, every time. You need to be able to identify. Top of the hill. This is the point where all the reactants are separated and they're ready to form those products.
Right.
They could be in some weird arrangement that is not written in the chemical equation.
It's the moment that you're at the tipping point on the roller coaster.
And then all of a sudden it can go without any more energy.
Right.
I don't have to add any more now. It's got everything it needs and down it goes. I like to think about pushing a shopping cart up the hill.
Right.
I got to add energy to get it all the way up, and then I can just let go.
Get to a certain point, you can let go.
Or it's going to go by itself.
Right. Climbing up one side of a hill to go sledding down the other side.
There you go.
I hope you're climbing up the short side of the hill.
That activated complex is that point where I put in as much energy as I need to get it to go by all by itself. Yep.
So the activation energy itself is the amount of energy from the baseline where you started to the top of that hill to reach the activated complex. How much energy do I have to put into this match to get it to strike and burst and combust? Right? If you strike a match and you don't do it right, or you don't hit it hard enough, it doesn't burst into flame. You didn't put enough activation energy into it, right? If you don't light the firecracker, you can't rub the wick on the firecracker and all of a sudden it bursts into flame. You need to touch a flame to it to get it to activate and start to fizz and pop and boom. Off we go.
Catalysts are special. They provide the reaction with an alternate pathway.
Mm-hmm.
They are not consumed, and they do not affect the delta H or the heat of the reaction. We will show you how to add this into the potential energy diagram. It's got a special line, and you'll see that the line for the potential energy of the reactants or products does not change.
But the activation energy does.
That's
and
right.
the activated complex
That's why it
does.
makes it go faster, because I need less energy.
It's like tunneling through the mountain instead of climbing over it.
Kind of. We've had some good
You still get
analogies
from
about
point A to
catalysts.
point B, but you took less energy because you went through the tunnel in the train tunnel instead of climbing up over this big hill or going all around. Anyways,
Overall heat of the reaction.
you got to know this equation because it's not given to you.
Third time we've seen it.
Potential energy of the products, so whatever's on the right side of the arrow, minus the potential energy of the reactants on the left side of the arrow. These are not overall affected by the catalyst because the catalyst only gets you from point A to point B through a shortcut. You're still going from point A to point B at their particular energy levels.
Correct.
But the catalyst makes it a shortcut, so you get there faster. Good. Let's draw some pictures and label them up.
So this is an endothermic reaction. I know that because I see the right-hand side is higher. So can we start with the potential energy of the reactants? That's right here. Can we draw an arrow down to the baseline, please?
No, it's this line right here. It is 20.
Well, I get it, but it's measured from 0 to 20, and we see them
That's
those
true.
arrows all the time. So can we just put in an arrow up and down for that for me?
So it's this.
There we go. From there to there. And the reason why we're just going to start this off right now. Do you see the dotted line, guys, on the curve?
This is a continuation.
That's a continuation of that point. So if that arrow that Mr. MoNaCo drew with those two heads is on the far right-hand side from the bottom up to that dotted arrow,
It might also be written over here, too.
then it's still the energy of the reactants.
Right. Even if that arrow's moved anywhere on this x-axis, it's still measuring from 0 to how much energy the reactions have.
So this is why I need you guys to understand very specifically. The reactants generally are on the left-hand side, and this piece here is the potential energy of the reactant. So let's keep that.
I'm just going to...
Okay, good. Clean it up a little bit. All right, good. And then we'll get rid of the one on the right, and we'll go right to potential energy of the products. Does that make sense?
Energy? If you had to put a value on it for this particular picture, Mr. Milks, what would the potential energy of the
Well, according to the graph, it butts right up to 20.
20
so-
kilojoules per mole.
That's what it is. So let's do the potential energy of the products, because that seems to make sense. So the products are over here. And so the line is going to go from the baseline 0 up into the line of the chart that represents the products. So now, again, notice the dotted line goes all the way across. I can see that it's now 50.
This arrow could be written anywhere along here. Heck, it could even be over here somewhere.
Right. That's the tricky part. We don't know where that arrow is going to be, but we know where the products are, and they represent that dotted line as them.
So this product has 50 kilojoules per mole of energy.
Yep.
Fair enough. What else do we got to know here?
Well, do you want to do activated complex, or do you want to do delta H?
Let's do delta H because we have the energy of our products and the energy of the
we
reactant.
know that I have to do the
The
potential
difference.
energy of the products minus the reactants. So if I did that, wouldn't that be the space in between the two?
Right. So it would be literally 50 minus 20. That's 30.
Right.
And so the delta H, the heat of the reaction, the overall change is right here.
Between those two lines. So again, that double-headed arrow could be anywhere left and right on this graph. It's generally not right in the middle because there is one that's specifically generally right in the middle. We'll see that. Because there's one where it can only be, well, no, can't say it can only be. But
That arrow could be drawn anywhere along here.
yes. So in between the two, I see that, look, this double-headed arrow is going between the line that is the products and the line that is the reactants. Hey, that's the definition of something, isn't it? The difference between the products and the reactants. Oh yeah, delta H.
Delta H, right there.
So we need to be able to get that. That's one of the most important things out of all these graphs.
Two more things we got to do?
Well, we have a few. We have activation energy in the
Okay.
forward reaction, or do you want to do the activated complex first?
Well, I'll put a star.
At the activated complex?
Hey, look what I did.
With the star, you made an A.
Yay!
No, a lot of times we will see a double-headed arrow here
Yeah.
for the potential energy of the activated complex itself. So we could see that.
So you might see an arrow that would go from 0 all the way to the top.
That is the potential energy of the activated complex.
Right, that's
In
how
this
much it has. In this case, it's 100 from this graph.
Right. And now the activation energy is the energy needed to get from the reactants to the activated complex.
So actually, this amount right here.
But notice it doesn't go all the way down to the bottom because it's got to stop at the energy of the reactants.
And I'm going to label this one in parentheses, forward.
Correct.
Why would I do that?
Well, because forward is going from left to right. So if I start on the left-hand side, notice the hill is really large.
Yep.
I got a large activation energy to get from the reactants up to the activated complex. But if I were to reverse the reaction and start at the products and go backwards, the arrow would still stop at the top where the activated complex is. But notice my starting point is different because I'm starting at the product side and going to the reactants. So here my activation energy is actually less. And it's intuitive because look at the hill. It looks easier to get up. It's shorter.
I think we have one more thing to put on this graph.
Okay, you tell me.
The effect of a catalyst.
Ooh, change colors.
Yeah, I should do that.
So when I provide a different pathway through the mountain, I'm going to use a dotted line. Notice it's got to start where the reactants start, and I start where the products start, or end where the products start, and it's going to look like that. And now notice, everything where there was an arrow touching the top line, the activated complex line, every one of those arrows would shift down. So you're going to see questions. If I add a catalyst, which one, what of these values am I going to change?
You're going to change the activation energy of the forward and reverse reactions.
And the potential energy of the activated complex. That's it. And that's it.
Because the heat of the products and reactants doesn't change.
Notice the delta H is still right where it would have been. Yep. That's key.
So this was an endothermic diagram because we started out with low energy and gained more.
Correct.
So let's show an exothermic.
Sure, and guess what? They're all the same.
Same labels are going to go in.
Yeah, so we'll do it a little faster.
Yeah.
For your sake.
Cool.
All right, so notice I started at a higher energy and ended a lower energy, so energy was given off. So the potential energy of the reactants, and again in the forward direction, is going to be this line that Mr. MoNaCo is drawing. Products on the right-hand side, notice it's going to be smaller now. Now these values are specific, and this is why we subtract products from reactants, so I get the correct sign. Okay, the activated complex is a noun. It's that single point at the very top of the hill. It does have a potential energy. You can draw it right down the middle. No? Okay, not down the middle, but okay, that's it. That's the potential energy of the activated complex itself. Okay, we need the most important piece on all these diagrams is the delta H. That is the difference between the products and the reactants. So it's always in between these two dotted lines. Very good. And now we need activation energy forward and reverse. So forward is from the reactants up to the top of the hill. And the activation energy in the reverse direction is going to actually be from the products up to the activated complex. And notice it's flip-flop from the other one, is from the other graph, as opposed to magnitude, how high these or how long these lines are. Here the forward reaction is shorter.
One more thing.
One more thing, a catalyst. So again, dotted line, kind of mimic the hill, if you will, but it has to have the same starting point and same ending point. And the effect of the catalyst will affect every arrow that's touching that activated complex, because as you can see, we'd have a new activated complex.
Different orientation. So there it is. The parts of the PDE diagram.
So now you can have some practice labeling these things up. And I would practice, and it's going to take some before we're done. So know how to label it.
All the parts.
No
And
matter
by my
where
count,
it
there's
is.
1, 2, 3, 4, 5, 6, 7, 8 or 9 parts of this graph.
Yeah, and you need to be able to label every one of them, and at a quick glance, tell me if it's exo or endothermic, the reaction.
And the way that you can do that is exothermics go downhill.
Yep.
And endothermics go uphill.
Uphill. They take energy in. That's it.
That's all there is to it.
All right, guys. See ya.
Bye.